My name is Brendan McKenna. I'm the Eastern U.S. Business Manager for SolidCAM. With us here today, we have Ken Merritt. Ken is our Senior Application Engineer. And as Sean had just mentioned, also we have Sean Maimutas. He's the company COO, so I have to make sure that I'm on my A game today. and
I can mess it all up. It's no problem.
Oh, yeah. Got to watch the ums and the ahs and the stuttering and, that kind of stuff. So, but again, thanks a lot for joining us here today. We really do appreciate your time. And what we're going to do here is we're going to run through our live iMachining presentation. There's a lot here to absorb. There's going to be an awful lot of information that's kind of presented here today. But by the end of this presentation, you'll hopefully clearly see the rewards of iMachining and the power and versatility of the product as well. So what I'd like to do is turn it over to Ken here. Ken's going to run through some PowerPoint information here with you, some technical information, and Ken, if you wouldn't mind, maybe we'll just
certainly
just dive right in here.
Okay, we'll do. Well, thanks again for joining us, guys. Today we're going to be talking about iMachining, and again, this is not a sales presentation at all. We're going to be digging in deep on some technical stuff. What is iMachining? You're going to see it's a really unique system. One of the things we really like to say is, even the fastest sports car in the world is worthless if you don't have any headlights and you can't see where you're going. And so one of the things about iMachining, we have patented the iMachining wizard, and it really makes things much easier to manage in the system. Now, I'm going to get into some pretty technical explanations of what's going on here, how it works, why it works, and so forth. But before we go into that, Brendan, what I'd like to ask you to do, this is kind of some pictures of the wizard and how it works. Can you give us kind of a customer's perspective on this? Not the technical side of it, but just what are some of your customers saying about whether or not this is easy to use?
Yeah, it's a great question, Ken. And really what the feedback that I always get from my customers is that, again, just like you said, they're amazed at how easy it is to use with all of the technology that goes in behind the scenes. And obviously we're going to take a look at that much deeper depth later in the presentation. But, it's funny, I get phone calls all the time, with customers. They're just saying, am I doing this right? Because it's so easy. They look at it and they think, okay, well, I just adjust this slider bar and that's kind of all I have to do, maybe just assign a tool. And yeah, and it's amazing. And then, the flip side of that too is I have a lot of other people calling me up saying, can you make the slider bar go to, like 14? Can I get more out of it? And it really is
we'll
funny.
Get into some of that.
Yeah, and so that's really the feedback, Ken, that I get the most from my customers. Again, it's really the ease of use, but they're just amazed when they see the results, the resultant toolpath. It's just it's really it makes my job pretty fun when you get those kind of phone calls.
Yeah, pretty cool. Well, hey, we're going to start out a little bit different today than we normally do. So we're going to do a challenge. Brendan, tell us a little bit about this challenge, and then I'll kind of give them some technical information on it.
Yeah, absolutely. This is something new that we're doing, and we're trying to, we're trying to kind of, set up a challenge for the people that come in and they take a look at iMachining. A lot of times they really kind of don't believe it. So we're going to throw out a little bit of a challenge today, and we'll tell you a little bit about what the challenge is and what's on the table here. You can see that this particular part, just a simple drawing, it's 1018 cold rolled steel. We're going to use a 1/4 inch 3-flute carbide end mill to cut this part, and we're going to be cutting at a depth of 625. Now, some people might look at that and go, well, hold on a second. You're going to bury a 1/4 inch tool at 625 deep in steel?
2.5 times diameter?
Woohoo! Yeah. And so, but we just want to go ahead, and I'm sure, you can see here it says guess the cycle time. Well, I'm sure many of you are probably saying, well, there probably won't be a cycle time. The tool is just going to break. Well, it may or it may not. So what we'd like you to do what we'd like to have you do, you can notice in the GoToMeeting, the GoToWebinar pane.
Josh is asking a question. He's like
Sure.
RPM, so he's asking spindle speed, which is going to vary a little bit, but maybe you can address that, Ken.
Well, we can't get into that right now. We need you to guess first as you're looking at this. We want everybody to guess the cycle time. Just if you were to take a part like this, you see the sizes here on the screen, and you were going to use a 1/4-inch 3-flute end mill in 1018 cold roll steel, and you had to cut a full 5/8 of an inch deep. Whether you do that in multiple steps, whether you do it in one step, give us your best guess at what you think the cycle time is going to be on this. And the winner is going to win some money. Whoever's closest.
And it's not like Price is Right. You can even go over. It's just who's closest. Who's closest.
Yeah,
and we have $500 on the line here, so this is not trivial.
Absolutely.
At least it isn't for me because I'm the one signing the check.
So I think Josh is predetermining what we're going to shoot for here. But hey, make sure you put your chat question in only to the organizer. Don't put it into all attendees. We don't want everybody to see what everybody's guessing. We want everybody to take a realistic guess at this, and then at the end of the presentation, we're going to cut this part, and we're going to whoever's closest, we're going to give them $500. So we're going to take just a minute here and let everybody get an answer in. So several people in here, so we'll just give a few minutes for everybody to think about it, and then make sure that you get your best guess into the chat window addressed only to the organizers.
It looks like we've got an answer here from Josh.
Mm-hmm.
And we're just waiting for a couple of others here.
Okay. All right, we got a few more coming in. Great. All right, and everybody, like I said, we'll give you another minute or so to think about it. I know this is kind of a challenging question. Just kind of looking at it, that's an island out in the middle. So we got to go around that island, plus we got to get all the rest of the shape out of there. And this is in a 3x5 block. So, and what we're going to do is, I've got another part we're going to cut first that's a part of our presentation, and then at the end we're going to come back to this part. We're going to throw another block of steel in there and rock and roll on this so you guys can see what it does. So just another minute to let several other people here get a hold of it, and we'll be ready to go. Looks like we've got several answers in here now, and if you don't get in an answer before we start off again, we close this off, because once we go into the presentation, it's not fair. Now, the other thing we want to make you aware of, going forward, we're probably going to do this in another web presentation down the line. But in order to be fair to everybody, if you've been in one of these web presentations and you've already taken a guess, we're going to do different parts and set things up differently and so forth to make it a little bit more tricky. But you're only eligible if you've not been in here, and if you're not a customer who already has iMachining and knows how all this works. So we'll try to keep it as fair as we can.
Yeah, exactly, Ken. That's really, I wanted to just reiterate that there's, it's basically limited to one entry per person, and there are no repeat entries as well. So
yeah, exactly. So, all right. Well, I think we're getting close here. Looks like we've got most everybody has entered their values in here, and it's a pretty wide range. That's good. So we will give it just another couple of seconds here, and we'll get started. Well, maybe if I can leave the screen. There we go. All right. So guessing is closed out at this point, and we're off and rolling. All right, well, I'm gonna talk a little bit about iMachining in the real world and what it actually does. But to start this off, see this part on the screen right now, this little coin dish type of a cavity mold, the one here over on the left. This is what we're going to actually cut today as part of our standard presentation. We want to show several things. iMachining's 3D roughing is what we're going to be showing you today and how it works. and I want you to pay attention to the scalloping and how well it finishes out the part. But you should have two screens on your display. One of them should be the camera inside the machine, and at this point you should see my hand coming into there. Okay, and then the other one is going to be, of course, the PowerPoint presentation. Go ahead and minimize. You should have a slider bar between those two. Slide the bar over to make the camera view inside the machine as large as is comfortable for you. And after this is done cutting, we're going to come back to that PowerPoint and talk about the science of what you're seeing here. So everybody ready? Let's go ahead and go. And Brendan, are you seeing the camera as well as the PowerPoint?
Yes, sir. Everything looks great.
Okay. And here we go with the cycle start. All right, now I want to talk a little bit about what's going on here as it's cutting this. One of the things you'll see, we're helixing into the material right now. iMachining does support pre-drill locations, but for these presentations, we like to show you that, hey, we can also just helix that tool right on down to 625 and take off cutting. So we're there now. Spindle is up to 10,000 RPM, and we're running at anywhere between 75, 77 inches a minute all the way up to 100, and I'm seeing 170 inches a minute there as well. So pretty aggressive cutting for a tool, quarter-inch tool that is 625 thousandths buried in this 1018 cold roll steel. Now you're going to see several things happen here. What you're seeing right now is a little interesting. We're getting some vibration on our camera. Sorry about that, guys. Notice that reposition move stayed down inside. One of the things that's very unique about iMachining is the fact that we are continuously updating the automatic stock remaining definition during the runtime of the algorithm. So at each movement of the tool, the algorithm knows where it is safe to move the tool with regard to the stock remaining. Okay? Now, what that does for us is we don't necessarily always have to come up to the rapid clearance plane to be able to reposition the tool. What that allows us to do, now I want you to think about something as we're working with this. On almost every machine out there, when you switch from a G1 to a G0, there's a momentary pause in the controller, and then it switches and it'll go into the G0 rapid mode. So it rises up, repositions, come back down. Now it has to switch from G0 back into G1. And again, you're going to get that momentary pause. Well, that doesn't seem like much until you get about 1,000 repositions in a part, and all of a sudden you've got an awful lot of time added onto that part just in repositioning the tool. Okay? What we're doing is we're keeping it at a G1, and we're utilizing the high feed rate of the machine to reposition that tool so that we don't have that pause going on every time that we're repositioning. And we're minimizing the amount of movement that we're doing by keeping it down in the area that we're cutting instead of always returning to the R-plane.
You know, Ken, I think one of the other things that's worth noting here as well is, you know, as people are taking a look at the toolpath itself, there might be some people out there saying, well, you know, I think I might have seen this before. You know, I think I might have seen,
sure,
you know, True Mill does this or Dynamic Mill does that, or, you know.
Bear with me for just a moment. I'm going to reset this camera just a little bit, see if I can get rid of some of that vibration.
Sure, absolutely.
So go ahead and talk.
Yep, no problem. And, you know, again, I just want to reassure everybody that you certainly haven't seen anything like this before. iMachining is a patented technology that was developed by SolidCAM. We actually have a tenured professor who is employed by SolidCAM who has helped develop this product over the last, what's it been now, 5 or 6 years, Ken? A little bit more than that?
It's been almost 8 years now.
Okay. Okay. And, you know, so again, this is very unique to what we do here. And there are a lot of things that really make this a very powerful toolpath algorithm, and again, we'll see a lot more of that as we get into the technical portion.
Okay, that looks like that might be holding up a little bit better. We don't have near as much vibration on that camera. Sorry about that.
Looks pretty good, Ken.
Now, what we're doing here is what we call the staircase removal. Okay, we're still roughing the cavity out, but we're starting from the bottom of the area that we just cleared, and we're working the tool upwards so that we're reducing the staircases as we take the material out. So we don't have to go in and do roughing at shallow steps all the way down, create a whole bunch of really nasty staircases, and then come back and try to minimize those staircases like a lot of other people are doing. We're actually making that cut all the way down at the bottom and then just kind of working our way back up the wall. And one of the things you're going to notice here as it's doing this is, again, those reposition moves are very optimized. Notice that it's working in a particular area before it works in other areas. That way we can optimize the movements into a regionalized, controlled area. Now, as we get deeper and deeper into this, you're going to see that regardless of the angle of the surface, the scallop height of the staircases is going to be the same. The algorithm automatically looks at what we call the inclination angle of the surface and computes the Z-step height to make sure that the maximum staircase offset is controlled and is uniform throughout the part. Now, some people really don't understand all the depth of why that is important, okay? When you have non-uniform staircasing in a roughing operation and you come back with your finishing tool is going to see an uneven loading and unloading of the tool. Therefore, you're going to get different flex against the surface finish, and it's going to create different grades of surface finish, if you will, okay? Most people over the years have resolved that issue by, of course, running a semi-finished tool path that's a much coarser step over, but reduces the remaining stock to a fairly consistent level over all these surfaces. And that alleviates that problem of the unloaded, the uneven loading and unloading of the tool. One of the cool things about iMachining is it does that all within the roughing operation. Now you're going to see today, I'm going to go straight from this roughing operation directly into finishing tool paths, and we're going to result with a very nice surface finish on this without having to waste the time to do that semi-finished cut. So not only is iMachining very, very fast and removes a lot of material very quickly, but in many cases it can basically obsolete an entire semi-finished pass. Think of how much cycle time that's going to save you on each part. Okay, so we're getting pretty close to being done with the finishing or the roughing here. You'll see this is a D-slot trochoidal channeling move that it's doing here to clear the area behind this island. And you can notice the way the tool is moving, it's never over-engaging the material. Okay, we're always moving the tool so that we never violate the maximum angle specified by the user. I believe in this case we were using 20 to 50 degrees. Okay, and we use a variable angle so that we can allow that tool path to morph. And I'll get into some of the physics and science discussion of that in just a few minutes in what we call a morphing spiral and the difference between that and the D-slot trochoidal or parallel offset style mode. Okay, we're almost done with the roughing operation. You can see it here doing the spiral morph. Notice the tool is never repositioning here. It's always making a cut. Okay, a couple of final finish roughing passes here before it goes into the flat surface finishing. And when it does that, I'm going to turn the air down just a little bit, and we'll go on talking about the science.
Ken, did we lose you there?
Yeah, I don't hear him either.
Yeah, I think he might be having some headset issues here.
That's what it sounds like. I wonder if he's aware of it. Probably not.
I'm going to get a hold of him right now. Trials and tribulations of technology. The beat marches on here.
It does. Okay, so again, we're coming live from Ball Ground, Georgia, where Ken is. So it
Brendan,
seems like we had a yeah, we can hear you now.
Yeah,
okay, great. Sorry about that.
Second there.
I've got to close Skype out. It kicked me out again. Sorry about that, guys.
Not a problem.
We love Skype ever since Microsoft took it over.
Oh, I tell you, ever since Microsoft took it over, I'm ready to throw it away, man. Unbelievable. Sorry about the technical difficulty there. So how much did you?
Famous expression, Sean? I'm sorry. What's that famous expression, Sean? Of Microsoft, where good software goes to die.
It was to die.
Exactly. Okay, we'll keep just enough air on there to blow the chips out of there, but I don't need to listen to all that noise. So where did you lose me?
Just before the, you just said you were going to get into the technical portion of the presentation, Ken. So.
Okay, good deal.
Yep.
All right, well, while this is doing the finishing, this is a 1/4-inch ball tool. It's going to do some Z-level finish cuts and do some other things around here. While it's going through all of this, just go ahead and let's drag that slider bar back over and make this a smaller window on the camera inside the machine. I want you to go ahead and kind of keep an eye on that throughout this presentation, but let's go back into the science here and we'll start talking about what makes iMachining really do what it's doing. All right, here's the key to all of this, okay? iMachining is all about the science of cutting angle. And what that means, basically, is we're going to control how the tool is engaged into the stock material by controlling its cutting angle from a minimum to a maximum angle range. Now, one of the biggest questions in this industry that I've run into is, are we really cutting metal? And the answer to that is an absolute no, we're not. It's a physics function known as plastic deformation, and this is really what it looks like. This video is showing a 35-degree turning insert that is passing through 1018 cold roll steel, same thing we're cutting today, and you can kind of see the plastic deformation line here as it's chiseling this material out of here. You'll notice underneath, you'll see this kind of bending of the material and returning back to its natural state. That's a function known as elastic deformation, the ability of a material to be deformed, but as soon as the pressure is released from it, it will return to its natural state. Obviously, along this line up here, that is not happening. Okay, this is true plastic deformation up here, and you can see the chiseling away of that material. So it's very important to kind of keep that in mind as we're talking about the various physics properties and mechanical functions of what we're going to be doing with iMachining. Now, cutting edge velocity has a great impact on the ability to carry a heavier chip thickness. All right, and so I want to kind of get into that a little bit. The cutting edge velocity is how fast the flute is actually moving through the material. Now, the higher the cutting edge velocity, the lower what we call the latent energy of plastic deformation. And an easy way to look at this is to think about a sharp knife on top of a tomato. If you take a sharp knife on a tomato and you push it straight down, you're going to squash that tomato. Yeah, it might cut it, but the pressure on it is going to squash the tomato. Whereas if you take that very same sharp knife and you drag it very fast across the tomato, it'll just slice through it, no problem at all, and it won't deform the tomato in any way, shape, or form. And so that kind of illustrates for us that as we increase the cutting edge velocity, we decrease the latent energy of plastic deformation. And that's not a direct inverse linear relationship or anything of that nature. I'm not a mathematician, so I don't know the exact mathematical ratios or anything like that. But in practical exercises and watching spindle load meters, we have noticed over the years that up to a certain point, the higher we get the spindle speeds, the less the tool load is on the spindle, okay? Now, when the rotational velocity of the tool is in line with the forward velocity of the tool, and we're cutting over here on the right-hand side of the tool, we'll have a pressure vector that's pushing on the inside of the flute like you see in this picture. Now, that's really important because that tool is designed in the way it's ground to be able to handle that pressure. This internal concave grind here is designed to curl the chip and eject it, okay? And the outside curve here is designed basically to take that pressure and redirect it back into the core diameter of the tool. And that's what stabilizes this tool through its cut. Now, the pressure vector stability is very, very critical to the integrity of the flute. And when you have a pressure vector that is completely unstable, we oftentimes see the tool fail with what we call catastrophic flute failure. Now, why is that and what's happening here? Well, we have two different modes of cutting when we're in a general traditional style toolpath. In a traditional toolpath, we have these sharp angles of change here that are known as what I call compression zones. And these are the areas where the tool has to change direction abruptly, creates a condition where the tool is overloaded in the cut. And as you can see by this picture here, we're in a full slot cutting mode, okay? And that winds up leaving us in a situation where we have chip thickening on one side and we have chip thinning on the other side, okay? Now, as the pressure vector moves through here, you can kind of see that what's happening at the beginning of this cut on the left-hand side, the pressure vector is almost directly opposing the travel direction of the tool. And therefore, it creates a linear or bending deflective force on that tool, which is not good. And as you can see, by the time it reaches the 90-degree quadrant, that force, of course, the chip is thickened through that travel. And that force is now pushing almost 90 degrees to the direction that the tool is traveling, and it's at the thickest portion of the chip, which is the highest level of the latent energy of plastic deformation. The other thing that this causes on the left-hand side of the tool here is that as the chip is rolling out, as it's being chiseled away, it's actually curling up into the direction that the tool is traveling. And this creates a condition known as chip compaction, where we wind up having the chip being bunched up against the tool and therefore conducting all of the heat that it's taken out back into that tool. And that causes us problems and doesn't, it kind of restricts how much surface velocity we can actually put on the tool. Well, one of the worst things that happens during this process of the flute traveling through the left-hand side of the cut over here is something known as pressure vector oscillation. At this point right here, at the absolute 90-degree quadrant, relative to the direction of travel of the tool, the rotational velocity, or I should say the effective rotational velocity, as it applies in the mathematical equation, the relationship, the ratio of rotational velocity to forward velocity, that effective rotation velocity becomes zero for an instant in time. And at that moment in time, the pressure vector actually flips to the outside of the tool and is pushing inward on that flute instead of where it belongs underneath. Now, that only happens for a moment in time, but it's devastating on a tool, okay? Now, we talked about cutting angles a minute ago. We work with a cutting angle range of 10 degrees to 80 degrees. That's the maximum range in our algorithm. Why the 80 degrees? Well, we noticed through practical testing and just, working with this and looking at the machines, feeling them, looking at spindle loads and everything, somewhere between 85 and 90 degrees, depends on the ratio of rotational velocity to forward velocity, we begin to see that pressure vector oscillation begin. Now, it never really fully flips to the outside like you saw earlier until right at the 90-degree quadrant. But above 85 degrees, we begin to pick up more harmonic vibration being generated by the move, by the tool cut. And so we've kind of looked at the efficiency of the tool path between 80 and 85 degrees, and it's pretty negligible. So we decided to limit it at 80 degrees because that keeps the tool out of that condition where the pressure vector oscillation begins to generate harmonic vibration, okay? Now, the 10 degrees at the bottom end, remember that picture we showed, that video we showed in the very beginning of this, if we can't get the tool underneath the material, then we don't really get that chiseling effect working. We actually sort of bounce off the material, and we cause what's called burnishing of the cutting edge, dulls the cutting edge, basically. So we want to stay above 10 degrees, but below 80. Now, in general, depending on the material you're cutting, steels, I generally work between 20 and 60 is the max. A lot of times I'll bring it down to 50 or so. It just depends on the hardness of the material. The harder the material gets, the more I'll bring the angle down. If I'm working with, aluminum or something like that, I'll take it all the way up to 75. I've even gone to 80 degrees sometimes. So kind of keep that in mind as you're thinking about what you're doing here. Now, in a traditional toolpath system, the toolpath is basically offset parallel racetracks, okay? Because of that, it creates all these compression zones that I was talking about where the tool has to abruptly change direction and therefore winds up in an over-engaged condition like you see in this picture. Because of the linear deflective forces that have been put on the tool at that point, we've always limited the depth of cut to 1/2 times the diameter to maybe 3/4 or 1 times the diameter depth of cut. Pretty much all anybody's ever done for the last 30 years. If you go any deeper than that, you really got to slow the feed rate down, okay? But what that means is the whole rest of the tool flute is not being used. So we're basically just throwing away all that carbide. Now, for years, one of the solutions was what they call a standard trochoidal move, basically orbiting the tool into each of these compression zones so that we alleviate some of those pressures and some of those negative influences on that tool. Wasn't really the right way to do it, but it was all we had for several years. What we've done with iMachining is we've come up with a completely new tool motion algorithm, and we're basically changing the way we move the tool. You may have noticed that in the live cut. This is what we call D-slot trochoidal. Now let me walk you through here. Let's take this cut line right here, kind of walk the tool through this cut line right here, and you'll notice that as it gets down to this edge here, it goes into a tangent helical move where it actually lifts off the floor, does a high feed rate repositioning move over to here, and then helixes back down in for the next cut. But notice there are no non-tangent alignments in this toolpath. Everything is being done in a tangent motion, okay? Another thing we do is morphing spirals. Now, morphing spirals are extremely powerful and extremely efficient because within the angle of the range of cutting angle, I should say, we can morph the toolpath from one shape to another without ever taking the tool out of cut. We don't need to reposition it, okay? Now, if it's necessary to go beyond that angle range that's specified by the user, then of course we have to break out of the cut, reposition the tool, and come back into the cut. But where we can keep it in that spiral morph, we can be much, much more efficient because if you think about it, D-slot trochoidal and the repositioning strategies are great strategies. However, up to 50% of that move can be a repositioning move. So it's in the air doing nothing for you, all right? Now, in order to support that, you can kind of see the difference between the two types of tool paths. Instead of doing this, we want to get to this spiral morph. But in order to support that spiral morph, what we have to do is we have to do a channel separation. This allows us to break this block here away from the main body of the part. Now, this, of course, is the D-slot trochoidal style channeling, and of course, this is doing reposition moves on every orbit. But that allows us to then take this big chunk without ever having to reposition the tool. Now, what's going on here? This looks a little bit weird. If we were to take this separation channel out this end at the same width, we would wind up creating a thin wall here. And because of the depth of cut, we're cutting at the full length of cut a lot of times. This would create a condition where the material could actually be pulled into the cutter because of how thin it is and how tall it's standing. And that would be a very dangerous thing. So we created a parameter in the system that is known as the thin wall thickness, and it looks at that, and if the channel would cause it to violate the thin wall thickness, it just expands the channel and takes that out on the way. By the way, sorry about the video. The camera looks like it's vibrating again. Let me see if I can stabilize that at all. Yeah, I'm going to have to find a way to stabilize that a little bit better. Notice what it's doing now. That's an 1/8 inch ball tool right now that's running around doing the fillets. in a very, very powerful rest machining strategy that we have. This tool is running at 16,000 RPM and 160 inches a minute in steel, and it's going to give us a beautiful finish. Let's go back in here and start talking about the separation process and what we're doing. There's something else that's very, very important. If we just did a separation channel along this edge here and separated this main block here away from the body of the part, yes, we could spiral morph this in one spiral to bring it into a single collapse point, but what that would do, if we allowed the range to be wide open enough for it to do that, that would mean that most of the cutting would be done along these long edges at or very near the minimum cutting angle. Not a lot being taken off the part at that point. And then, of course, as you came across these short ends, we'd be at or very near the maximum cutting angle where we'd have very efficient material removal rate. But most of it would actually be being done at a very inefficient material removal rate. So what we did is we came up with a way of looking at the efficiency of the spiral, and we created these separation channels that allow us to break it into more symmetric regions where we can do the spiral morph but keep the tool closer to the maximum cutting angle and optimize the efficiency of those spirals. Now let's walk through a traditional part here, a typical part with an iMachining style cut. One of the things we're going to do, whether it's an inside-out spiral or whether it's an outside-in spiral, we're going to try to preference spiral morphing. Now we can't always do that first chronologically, but it's our first priority, okay? And then what we do is when we have to deal with islands, we'll do the D-slot tricoidal to clear around those islands or do separation channels in areas as necessary. But then if it's possible, we're going to return back to that spiral morphing because it is the most efficient way to get material out of this part. And again, we'll deal with what we got to deal with. You know, different parts give us different things that we have to pay attention to. But when we can, we're going to return to the spiral morphing, even if that's only for a very short period of time. Now, at some point during the progress of a cut, you have no choice but to go into the final parallel passes. And these are the offset parallel passes, and they require us to reposition the tool. However, one of the things that we're doing dramatically different from anybody else in the industry is that we've got that range from minimum angle to maximum angle. And by the way, that's patented. And that allows us to actually morph the parallel cut and get a much longer cut and do less repositioning. You'll also notice we use what we call detour moves, like I was talking about when we were seeing the live cut, where we can keep the tool down and just simply reposition it at high feed rate inside the cut, knowing that we're safe because we're using offset boundaries from what we know we've already cut, okay? And so even when we do have to go into the final parallel passes, we're going to optimize that for you as well. And then, of course, we cover rest machining, getting rid of the remaining stock. If you wanted to cut this with a larger tool, come back in with a smaller tool to finish those areas where the bigger tool didn't fit. We do that very, very effectively with iMachining. iFinish is a very, very interesting module because most people don't think about this. You guys have all seen the diagonal lines in the corners and heard the chirp and the chatter when the model radius is very, very near the tool radius, okay? What iFinish does is actually analyzes the topology of the model for those over engagements, and it goes in and it picks those corners out first using the D-slot tricoidal down to the minimum cutting angle. And then it allows the contiguous toolpath to come through here on a finish cut and not over-engage, but also not under-engage. So we're not going to burnish the tool. We're going to wind up with a really, really nice surface finish through those corners. Okay, very, very powerful system for that. Now, we're almost done in the machine, and well, I wish that camera wasn't vibrating so bad. Sorry about that, guys. Let me put my hands on it. You can see how fast that tool is moving through that area, okay? And that did some amazing work in there. I'm gonna go ahead and reposition this manually. Let me roll this guy back out here for a second. We're gonna drop the spindle down. Let's go back into manual mode. I'm going to drop that spindle back down, and Let me get a wrench on this guy so I can move the camera. Brendan, can you guys still hear me okay?
Sure can, yeah.
Oh,
Everything
good.
looks good.
All righty. All right, let me bring this guy out here and just kind of point it straight down. And then let me walk the tool or walk the machine back underneath it for you. Okay, and we'll bring her back down to where we can see that. That should probably get us in the ballpark. Let me get it repositioned here a little bit. And let's take the X over to like that. Okay, so a couple things I want to talk about before we go into this video over there. Let me sprinkle just a few of these chips out here. One of the things we didn't really talk about while this was cutting, and it's one of the really important things, remember we were talking about cutting between a minimum and a maximum angle, all right? Well, most people, most CAM systems today are calculating a chip load. Chip load is computed at the 90-degree quadrant as the thickness of the chip per flute, per revolution of the tool, straightforward advance. What we calculate is actually chip thickness. We're calculating that chip thickness at the cutting angle. So if at any given point through the algorithm, the tool is at, say, 47 degrees cutting angle, the chip thickness is actually being calculated at that angle. And so as the morphing spiral runs and the chip runs between the minimum and the maximum angle, what we do is the programmed chip thickness is for at the maximum angle. So your feed rate, as the cutting angle goes down towards the minimum, we increase the feed rate so that we keep the chip thickness the same at that cutting angle. And so you'll see in the tool path, you'll see the feed rates going up and down, up and down, up and down all the time when the spiral morph is doing, or even the parallel passes are doing the minimum to maximum angle ranging. And what that does for us, if you'll notice, these chips are just extremely consistent. No matter where you grab them from in the cut, they're going to be very, very similar in thickness. And I mean micrometer style within tenths, okay? And of course, that's going to depend on, how fast your machine can respond to the feed rate changes. But on a good machine with a good response time, you're going to see chips throughout the entire cut that are within a tenth or two of each other, okay? Very, very stable chip thickness. What that does for you is that keeps a continuous and a very constant load on the tool. What's the worst thing we can do to carbide? Is shock it, okay? Whether that's a thermal shock from, hitting it in and out of coolant, whether it's a vibration shock from creating harmonic vibrations, or whether it's an impact shock by not bringing it into the cut smoothly, the worst thing we can do to carbide is shock it. It'll fracture the substrate, okay? So everything we're doing in iMachining is designed around keeping the load on that tool extremely consistent so your tool life goes up even though you're getting increased performance and productivity out of the cut. Now, the other thing I want to talk about in here, let me blow a little bit of that out. Good, chips all over the place, is the surface finish. Remember we talked about not having to do a semi-finished cut. Well, guys, take a look at this wall over here. Okay, you can see the mirror shine on that wall over there. I can run my fingernail up and down that thing, and I don't feel any vibration at all. I would venture a guess, and granted I don't have a profilometer here, but I would venture a guess that on this wall over here, on this wall right here, this one right here, these over here, we're running probably right around a 16 RA finish without having to do a semi-finish. Even on this shallow slope wall, and even though we're in 1018 cold roll steel, a material that's known for tearing and not being a very good surface finish, and we ran it dry, even on this surface here, I would venture to say we're under a 24 RA finish on there. We might even be closer to a 20, okay? And the part that's really cool is down here in these fillets, okay? All of these fillets where that tool was running at 160 inches a minute and 16,000 RPM, those are all easily a 16 RA finish down in there, okay? So even without doing a semi-finished tool path, we were very nice, smooth surface finish that's going to result in much less requirement for hand finishing in your shop. Now, go ahead and minimize again that screen from the camera and the machine, because I want to show you some things about lower performance machines. Today we're running a pretty nice machine, and I'll describe it a little bit here in just a few minutes for you. But I also want you to think about, you know, what do we do with the equipment that we have today, okay? And we want you to know and understand, iMachining is not dependent on the machine, and it is not dependent on the tool. It is actually designed to optimize whatever you have. So let's take a quick look at this video here, and I'll try to get through this pretty quick because I know we're going to run out of time with our challenge. This pocket over here, this is an old TM2 Haas tool room mill, open bed machine, you know, open column machine. It's been rode hard and put away wet. This thing's only got about 4,500 RPM on the spindle. We're only able to get about 50 inches a minute out of it before we start running into data saturation and hesitation and things of that nature. This is a 1-inch deep pocket, approximately 3 inches by 2 inches or thereabouts. The user, one of our customers out in Colorado, was cutting this with a 3/8 inch tool, and he was taking 50,000 step downs at 2,200 RPM and 18 inches a minute. And that was about all the machine could take. It was vibrating it pretty bad. By the time he got to the bottom of this, 2 hours and 26 minutes worth of cutting, 50 step downs, the bottom of that tool, the bottom 50 thou of that tool was gone. Okay? So he called us and he said, look, you got to help me. How do we do this better? So I showed him iMachining. Well, notice I'm running the tool all the way at depth. Not a very impressive video, but let me go ahead and roll it forward a little bit for you. Notice how we're all the way at full depth, and we're doing the iMachining. Again, not an impressive video because it's not a high-speed machine. But let's look a little further into this. Let's go a little bit further. Notice the color of the chips coming out through the whole time. Let's go further forward. It's got most of the pocket done right now. Again, look at the chips that are coming out of here. They're beautiful. Let's go all the way up to here to the end. Excuse me. Okay, notice again the color of those chips, and look at that. 7 minutes and 25 seconds to cut that pocket. Now what really blew his mind was I went ahead and cut 3 more pockets on this bar for him using this same tool. Remember, when he cut this pocket over here, 2 hours and 26 minutes, and that tool was done. The bottom 50 of it was gone. He could not, there's no way he could have cut another pocket with it. But the whole rest of the flute was unused. Okay.
Yeah, you know, Ken, and that's a great point, and I just wanted to jump in real quick. You know, again, really the whole purpose of this is to just reiterate the fact that, you know, iMachining can apply itself to either a brand new, you know, $500,000 high-speed machine, or it can take your existing machinery and turn it into, you know, 2 or 3 machines just because of the production that you're getting off of it. I have several of my customers. Exactly. You know, I have several of my customers who are still using, you know, they're using, you know, Fidels and Haas's and, you know, Boss 8s even, and they're getting far more production with iMachining than they ever could have. So, you know, it really, we want you to be able to take advantage of the current solutions that you have for machinery with the understanding that iMachining will make it more productive.
Right, exactly. And the other thing that I want to do here a little bit, I do want to give kind of a shout out to our partners. This is about the only sales aspect of this we're going to do. But Applied Machine Solutions is where I'm at right now here in Ball Ground, Georgia. And they're a Herco dealership. And again, we're not machine dependent, guys. Skip has been nice enough to allow us to use these machines to do these presentations. And actually, I'm pretty impressed with the machines. So I will say it this way. This is the machine we're running today. If you're in the market for a new machine, I would definitely keep these on the list of ones you look at. This controller is pretty unique. I really, really like the controller. I'm fairly impressed with the machine. 18K spindle, 900 inches a minute in G1. I'm actually contouring, I've done some contouring at close to 600 inches a minute, and it's been able to handle it. So not a bad machine. Again, not you know, advertising for them, but at the same time, I'd at least look at them. You know what I mean? A little bit about tools. Again, we are tool independent. I don't care if you use an AccuPro, you use a Z-Carb, you use a whatever, YG1, Mitge. whoever you're using, GW Schultz, doesn't matter to us. We're going to take and make that tool perform at its very best with iMachining. Okay. Now, you're going to get better performance out of, a YG1 tool or a Mitke than you're going to get out of an AccuPro. But iMachining is going to take whatever tool you've got, and it's going to up the performance way beyond anything you can imagine. Okay. But these are the tools we're using today. And I do want to, let me back up just a second. I do want to say a little bit about tool holding, because this is really, really important. And this next set of videos will kind of elaborate on that for you. Tool holding is a little more important than tool and machine with regard to how aggressive you're going to get with iMachining. If you're going to get as aggressive as I'm going to show you here in a few minutes, you got to have a good tool holding system. Now, I've put some tools into some very decent systems, Lindex Nikken, HPI Pioneers, Shunk, Big. I've used all of them, okay? Watch this video. This is pretty interesting. Now, we're doing some pretty crazy cutting here. This is a 10mm tool, 800 thousandths depth of cut in 1018 cold roll steel, cutting at 12,000 RPM, 350 inches a minute. I want you to watch this corner right here as the tool begins to kind of get going and move out here. You're going to see something very interesting happen. And this is a high-end milling chuck, okay? This is not a cheap piece of equipment here that I bought. We got a really good milling chuck trying to hold on to this cutter. But watch what happens right here. See that line up here? I mean, we're boogieing. We're at super high performance on this. Pulling the tool out of the tool holder, okay? So you've got to be careful when you're doing this stuff. You've got to use the right equipment. If you're going to get seriously aggressive and start really doing some high performance cutting, I like these RegoFix power grip systems. They have more holding power than the shrink fit holders have. Now watch this video. This is the same 10mm tool, same time, 14,000 RPM and 512 inches a minute. Same step over, the same 50 degrees cutting, okay? And I don't have any problems with it holding on to it at all. This tool holds on really, really good, and you can see how dramatic the material removal rate is here. We're getting some chipped out of here, okay? Very, very fast machining going on here. Now, I'm going to let Brendan talk a little bit about our website while I go change a tool and reset it, and we'll get ready for the challenge.
Certainly. So yeah, what we'd like to do is when people always ask us for more information, where can I find videos, where can I get more web content, or content about iMachining, and also the other products in our portfolio. Well, SolidCAM.com is really the best resource for that, obviously. You can see here we've got all kinds of information available to you. We have training videos. We have what we call SolidCAM Professor videos as well, where you can go and you can actually it actually gives you lessons. You can look if you're interested in probing, if you're interested in 2-axis machining, 3-axis machining, mill turn. All of that information is available to you right at SolidCAM.com. The other thing that I would encourage people to do as well is to go online and go to YouTube and search for iMachining. And one of the things that you'll notice there, you'll see tons and tons of videos that, in fact, many of them are not SolidCAM marketing videos. A lot of these are customer videos. They just take out their cell phone, and they're so impressed with iMachining, they'll take a video of iMachining and they'll throw it up on YouTube, and some of the comments that you will see there are pretty funny. In fact, there's some colorful language, so you might want to be a little careful.
Let's throw a disclaimer out there and say if shop language bothers you, be careful which ones of those you write.
Exactly.
You're watching.
Exactly. So, but it's really kind of fun. When you watch those videos, that's really what makes my job a lot of fun as well.
I love that one you showed me where the guy starts clapping at the end.
Oh, yeah.
It's classic.
Oh, it's hilarious. It's hilarious. At the end of the cycle, the guy actually was clapping and, applauding like he was at a concert or something. It was fantastic. So, and again, that's what really, again, just makes my job fun and exciting every single day. So But again, the website is a tremendous resource, and you can also, if you're interested in taking a little bit of a deeper look at SolidCAM, you can contact us there, and we'll have one of our representatives give you a call.
Okay, and bear with me just a few moments here, guys. I've got to reset
Sure.
a tool here.
I think one of the other things that I might have forgotten here, Ken, was just to mention, if you have any questions at all on SolidCAM or iMachining, anything about the product at all, there's a contact us number right on the website as well. Call our customer support guys. You know, we take a lot of pride, and we've put in an awful lot of work putting together one of the best technical support teams, I think, that's out there today.
Well, bar none, man. We got some good guys in there.
Absolutely. I mean, you know, the collective man years for, you know, in terms of machining knowledge and programming knowledge is just astounding. So if you do have any questions at all, just give the guys a call. They'd be happy to talk to you about your particular application. If you want to maybe just hear a little bit more about the product, or maybe even have one of the guys show you a couple of things, we'd be more than happy to do that. So we really do encourage you to to take us up on a lot of this information that we're putting out there. And again, because we do believe that this is the best solution, and we do believe it's it really is the way of the future in terms of machining.
Okay, we're just about ready for the challenge. Let me go back over here and get the other file loaded up.
One of the questions here that we had come up is this whole demo done on mills. So I'm assuming that he might be looking for some turning information, and we can certainly address that towards the end of the presentation.
Oh, absolutely.
So he was actually looking for mill turn information. So we can talk a little bit more about that as well.
All right, let me get this thing aligned.
You're a brave man, Ken, doing a live setup.
Yeah, now that you said that, I'll probably crash the tool.
Don't even.
Nice there.
That was a vote of confidence.
Yeah, I hear you. All right, guys. So we're ready to run the challenge, and now we can talk about the high and low guess. The low guess was 2.5 minutes, and that's a little bit aggressive. The high guess was over 17 minutes, and here we go. Let's see what it takes.
All right. Who's going to win $500? We're dying to give this money away.
Okay, now again, we're helixing down in. Now this is a Mitke tool, MITGI, which is the Midwestern Industrial Tool Grinding Incorporated. This is their 1/4-inch 3-flute high-performance tool with an Altin coating. Okay, and as you can see, it does a real nice job of getting that material out of there. Okay, now we're going to work our way around an island here. This is D-slot trochoidal channeling that we were talking about, separation channel, which will then allow us to go into a very high performance spiral north. Okay, now right now I'm running, I'm not even registering a spindle load. Okay, kind of give you an idea what you're seeing here. Chips are coming off, beautiful color.
Yeah, Ken, that's another really great point too. I'm glad you mentioned the spindle load as well, because again, just because of the algorithm and the way iMachining works, it's really it actually sort of flies in the face of what you would think of traditionally. A lot of people say, well, you can't bury a tool that deep without causing extra wear and tear on the spindle bearings and things like that. And it really is the opposite. It almost seems counterintuitive But
Yeah.
you can see here the amount of material that we're removing so quickly is just, it's amazing.
And in this spiral morph, I'm looking at about a 15 to 18% spindle load, okay? So it's really not taxing the machine very hard at all, and yet look how quickly we're removing this material, okay? And again, with just air blast, no coolant. All I got to do is make sure I get those chips out of the way. We don't want to run over chips, so I need enough air blast in there to blow the chips out, get them out of the way. The tool is thermally stabilized. And I'll tell you, when this thing comes up, you know, I'm not going to hang on to that tool, but I can touch it. It's not very hot. It's probably in the 160-degree range or thereabouts, okay? I mean, it's not something you want to just reach up and grab a hold of, but it's not going to blister you as soon as you touch it either, okay? The part is very cool as well. Now, you saw that go through some morphing spiral. Now it's doing the D-slot tricoidal. This is the parallel offsets because it could not machine all of this material out within the min-max parameters that I set for the cutting angle. But now it's getting it back prepared to where it can return to the spiral morphing, and you'll see that in just a moment. And then I want you to see, as it starts really cleaning it up, I want you to see some of the reposition moves down in here. Some of them are a little scary, especially at 1,800 inches a minute, you know, the high feed rate, or 900 inches a minute, whatever it is. I think it's 18 on rapid on this machine and 900 on G1. But watch some of these moves in here. Now we go back into the spiral morphing. Okay, so again, we're getting this material out very, very quickly. Okay.
Yeah, some of those moves, Ken, those detour moves they are a little scary, but it's you know, I'll tell you, when you look at it though, and you see how efficient the tool path is.
Oh, it's crazy. Yeah.
It's unbelievable.
Yeah, it really is sharp.
Yeah, I think we all remember the good old days of step down, do a pocket, bring it up, reposition, step down, do another pocket. Just like that video, Ken, that you showed of the old Haas machine there.
Yeah.
Those days are over.
Oh, yeah, absolutely. Look at these repause moves in here. I mean, it's just amazing how that tool moves around in there. But you can count on it being safe because the algorithm, like I said, at every step of the algorithm, we know exactly where that tool has been, and we know where that material is clear, and we can safely move that tool in what we call the detour move. Okay? So let me roll this guy back out here. And we'll just bring that tool back down. You can kind of see what we've got here. A little bit further. Kind of an optical illusion in the camera. It looks like I'm about to crash, but I'm not. Okay, but you can see how much material was removed out of there, and it was 4 minutes and 54 seconds. Okay, I mean, what an amazing cycle. Huh?
Every time I see it, it's just, it really blows my mind. I get a smile from ear to ear. It's amazing.
Yeah, it just is, it's crazy. So it looks like Josh, I think, is our winner.
Josh is the winner.
Yeah, Josh is our winner. So, Josh, if you would,
was 2.5 minutes.
Yeah, type into the chat window your full name, and make sure you're doing this just to the organizer, not to the whole crowd. But type in your full name, your mailing address, so we can mail you this gift card, and a phone number where we can contact you, along with, I think we've got your email. But
we have his email, and it will be a Bank of America check.
Oh, it is? Okay, cool.
Yes,
very cool. So yeah, go ahead and type your information in there for us, so that we have that. You don't know how to go just to organizer. You know, I don't either. Sean, you've got his email though?
Yes.
Okay. Send him a quick email, and let's see if it shows up there, and let's make sure it's correct. and then we'll just communicate through that with them and get a hold of his shipping, your mailing address that way. But
Okay.
guys, we ran over just a little bit because of the challenge. I appreciate you all sticking with us. If you have any further questions, like Brendan was saying earlier, please jump up on our website. There's plenty of contact information up there, how you can get a hold of us. We'd be more than happy to give you a personalized demonstration on the whole rest of the program. It's a very, very cool product. Works inside SolidWorks, full associativity. You don't break the SolidWorks model, you're not going to break our toolpath. So we think we've got something pretty special here. We'd love to help you out and get you guys using it.
Very good. Well, again, just as Ken said, we appreciate everybody's time here today. Thanks again. We really do appreciate it. We know you guys are busy, and we'll let you get back to work. But on behalf of Sean and myself and Ken, thank you once again, and we will be talking to you very shortly.
Okay, and Josh, go ahead and hang on for just a moment while Sean's validating that email address with you. As soon as he tells me we're good, we'll go ahead and close out the meeting.
Okay, it's been sent.
Okay, Josh, he sent it to you. If you would check your inbox.